of this semester in the famous experimental math seminar. I hope that all of you will come as many talks as you can. The next speaker is our own Nils Sloan. A very, very good talk, and the other good talks coming up. Everybody is welcome. On one condition, that no electronic devices are allowed in this class. Everybody knows that mathematics is a queen of science. Unlike physics, chemistry, biology, etc., that are empirical sciences. You do experiments and then you make theories, but still it's based on experiment. It's an inductive science. Mathematics is a deductive science. At least it was a deductive science for the last roughly 2300 years, when Euclid started the axiomatic deductive paradigm, and this is still the ruling dogma today. And this did a lot of good for a long time. I just finished reading a very interesting book that I strongly recommended by my former colleague from Israel, Tzvika Artstein. It's about the nature of mathematics and evolution. And his point was why mathematics is so hard for everybody. For most people, especially for non-mathematicians, but even for mathematicians. The reason is that in evolution, for most of the time in evolution, when we had to gather and hunt and survive, did not prepare us for the strict, axiomatic, Euclidean, rigorous logic. That's why it doesn't come naturally to us. That's why we had to artificially train ourselves. And even we great mathematicians, have to struggle. It doesn't come up naturally. And that's why the men and women in the street have so much trouble understanding what to us professionals is obvious. So formal logic is very, very unnatural, because it did not prepare us. Evolution was 1 million years since we came from our ancestors, and mathematics is only 2,000 years. But in addition to biological evolution, there's also cultural evolution. And what we learn is the education we get. So mathematics really, really blossomed with the cultural evolution of using the axiomatic deductive approach, not to be confused with the inductive approach. So the conventional wisdom was mathematics is deductive science, biology, chemistry, even physics are inductive science, experimental science. Of course, you make theories, you make conclusions, you use logic, but still it's based on experiments. I claim that cultural evolution did us good, but did not prepare us for the computer. Now that we have the computer, we have to change the paradigm. Euclid did lots of good. The Euclidean paradigm, modern mathematics, really, really did mostly good. Some of it became really, really over-specialized. Some of it became really like a religion. You start splitting hair and doing problems that just because you can do them. So it did all good, but by and large, mathematics did an okay job. But still, it can only do trivial things. If a human can do it, even a smart human like Andrew White or Christopher Perlman, it is not that deep. Let me give you now a statement that it's much deeper than anything that Andrew White ever did. Here is the following. Theorem. Suppose I'm walking on the straight line or staircase. It's very easy and classical to know if you have 2 steps, forward and backwards. So first let's review a classical theorem. The number of ways of a drunkard is a random walk. A drunkard, so you have the pub or bar starting, say, at I equals 0. And the drunkard at every step is goes forward and backwards. And after certain number of steps returns to the origin. So a number of ways a drunkard can walk and steps and return to the bar, to the pub, and return to the pub. Is not that hard. Can anybody tell me? Huh? Not yet, not yet. This is even easier. He's allowed to go either way. So it's okay to go 1, minus 1, minus 1, 1. So forward, backward, backward. So this is even easier. Yeah, he says 2n to the end. So that's classical and very easy. Yes. Sorry, 2n steps. If n is odd, of course it's 0. There's no way even a drunkard can walk an odd number of steps go back. Now if you include the condition never, suppose it's very, very dangerous for a drunkard to go to the left of the pub. This is a safe neighborhood, but here you get caught or something. And never, so, and if you add a statement and never return to, and never go to the left, never go to the negative, to the left of the pub. Then, as Simon said correctly, it is famous Catalan numbers A 0 0 0 1 or 8, right?
Right.
The most frequently occurring combinatorial sequence. And if you go to the OIA or OIS and you look at the thing, it's the biggest entry, right? Has many, many things. And one of the many things is counting this. This is no longer completely trivial for a human. And I know at least 10 proofs. Some of them are more elegant than the others. Today I will give another proof that in my humble opinion is the most elegant, but in most people's opinion is very, very ugly. So it's all a matter of taste. So this is classical. But now suppose a drunkard is not so. It's interesting drunkard. He's only allowed to walk. He sometimes feels energetic and goes 2 steps. So instead of the possible steps, so here the possible steps be minus 1 and 1. Now he has 3 options at every time. Either walk sorry, I want to make sure I'm consistent. Yeah. Either walk 1 step or make a big step. Or if you want walking a staircase, sometimes you feel energetic and you want to do. And you can also go back, if you go backwards, you can go 3. So you can make it in sequences. So this is minus 3. So that's okay, because it didn't go to the left. But it's not okay, because this is minus 2. So that's not okay. So of course you can actually list the first few. But suppose you want to know in how many ways can you do it with 10,000 steps. So let's call this sequence. It's not in slow yet. So maybe very soon. This is a brand new sequence. So with this set of steps, suppose you want to know this number, its computer is half a screen full. It cannot, maybe a screen, it's definitely less than, so it probably has it's less than 10,000 digits. I mean, well, less than 5,000 digits. So it's easy to describe this number. But compute this number exactly, not approximately, not using asymptotic, exactly. Here it is. It's a number that starts, yeah, here it is. I don't want to take the whole thing. So this fact that 8,000 is 388 632. And it very soon be available in my website. This fact is trivial. Contractually, it's trivial. In principle, you can construct all the sequences that many, find out how many of them add up to 0, and then find out exact all those that have a partial sums that are negative, that are good. So it's an algorithm. It'll take you that many, roughly, that many steps, but things, but that. I claim that this fact, that very soon available on my website, I don't want to print out the whole thing, it's like here, is far deeper than Fermat's last theorem. Because otherwise, Christoph Fermat will never be able to do it without a computer. And in my humble opinion, it's just as interesting. Not by itself, but as a thing. And the way I got it is not using anything fancy. I got it by using the most naive method, guess and check. Before we do algebra in middle school, you learn when you have a riddle, you just try it out, like Alice and Bob with apples in the abstract. So I describe it how. So in order to illustrate the method, I will prove this theorem. And indeed, guessing is very important, looking for patterns. So let me describe this method. It's basically looking at the data and finding patterns. That's what we all do. We generate data, we look at the pattern, and click, we find a pattern. But some of the patterns, most of the patterns, humans cannot just. So the usual mode of research, both in the sciences and in mathematics, is to look for patterns, make a conjecture, and then prove it using deductive logic. But sometimes the patterns are so complicated that no human can find it. You need IQ of 10,000 to do it, to find this sequence. So you can start to crank out the first 100 terms and see a pattern, and then basically I did it. But the computer has such a high IQ that the computer can look at the first 100 terms that are easy to generate by a naive program. I describe it later. And then look at the pattern, continue the pattern, and find it. But not like an IQ test to test whether your IQ is 110 or more. So anybody with IQ more than, even for example, art, you can find what's the next term? 13. Very good. And IQ 120, 1, 4, oh no, 2, 5, 10, 17,
26.
Yeah. 26, okay.
37.
Yeah. Matthew, what's the next one?
So 3, 5, 7, 9, so we need to add on 11, so 37.
Very good. And this is how really science goes. You look for pattern and continue it, and later on you can improve something. In fact, the great philosopher Ludwig Wittgenstein really liked this thing, and here is a quote from his philosophical investigations. Let us imagine the following example. A writes series of numbers down. B watches him and tries to find a law for the sequence of numbers. So here might you find a law with differences, or you could find that this is 1 plus n squared. If he succeeds, he exclaims, now I can go on. So this capacity, this understanding is something that makes its appearance in a moment. So for smart people, these things in a moment. But for more complicated things, a computer needs not a moment, even for a computer, 14,574 seconds. So I describe how to do it with guess and check. But before that, let me digress how Gauss could have done even better. We all know the legend of 7-year-old Gauss, that the teacher would want to have a peace of mind, so he told the students to add up the first 100 numbers. And he was very upset, and he was taken aback when 7-year-old Carl Gauss raised his hand and told him the answer. So you all know, probably, if not, look it up, the Gauss trick. I don't like this trick. It's the stupid trick, ad hoc trick, that only works for this. If the teacher would have asked him to do this, this trick would not work at all. So he was stupid. If Gauss would have been really, really smart, and maybe that's how he did it, I don't know, he would have just done a table. We define a sub n to be 1 plus 2 da 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 plus n, and make a little table. A of 0 is 0, a of 1 is 1, a of 2 is 3, a of 4 is 1 plus 2 plus 1, a of 3 is 6, a of 4 is 10, and factorize it. This is 2 times 3, this is 3 times 4 over 2, and you can easily guess an explicit formula just from the first few data points. Find a pattern, a polynomial pattern in this case, a sub n. So Gauss could have made a conjecture just by looking at the first few cases. And then generalize it, and then check it a few more. Since I don't like deduction, I only like induction. If you check it for 3 more or 4 more, it's pretty safe that it's true forever, and then plug in 100 and get the answer. So that's the same philosophy that I will do today. And while we illustrate the method by reproving the original one. The ugliest possible proof of this classical theorem, that the Catalan numbers. And here goes. So I illustrate it in some detail, because the same method works for proving much, much harder this. And this, you cannot get a formula for this. This nice formula is 12 factorial. You can carry it in your wallet, not even that. This is the formula. There is a formula for this set of steps, 1, 2, and minus 3. Here it is. Yeah, here it is. I tell you in what sense it's the formula later on, but it is a formula. It's a formula in the sense that once the computer has it, it can very fast compute A of 10,000, A of 100,000, and if you have more computer time, A of 1,000,000. So it is a formula, a complicated formula, a complicated that most humans will not be able to appreciate. Humans like simple things. And this is my meta-philosophical theory why the Catalan sequence is so popular. Why in the OIS the Catalan sequence has so many entries. Because humans do mathematics, and humans like simple things. And the Catalan sequence is the simplest possible sequence. It's not completely simple. So-called algebraic formal cause, algebraic generating function. But never mind. So let me now describe how to do this thing. So you look at all the walks, coordinate sequences. So that's not good. So the bar means negative. Okay. But not necessarily going back to the origin. And I give a weight. I assign a weight to such a sequence. First the length, 1, 2, 3, 4, 5, 6, 7, 8. Then the length of the walk. How many walks the drunkard to the power n. And then x to the power the destination. If you add them up, you get the destination. Well, the drunkard is located at the end of the sequence. So 0, 1, 2, 3, 2, 2, 2. So sorry, this is how many? Yeah, first example. So you attach and wait. So there's an infinite set. Look at the all infinite set, infinite quote unquote. Set. The empty walk. Walking. What? This is not good because you cannot walk. You cannot go negative. This is the next one. Then this is good. Forward, backward, forward, backward. And this is good. Forward, forward, backward, backward. So I look at all of them in the infinite totality of them.
Why is 1 there?
Right?
Why is 1 there?
Oh, 1 is okay. No. Now I consider the more general. Now I consider the more general set of walks. Well, you don't have to wind up at 0.
So why not 1, 1?
Yeah, 1 is okay too. Thank you. Yeah, thank you. Yeah, 1 is okay too. Sorry, thank you. Yeah. So all walks. So if the coefficient of x is 0, and then I do the so-called formal power series. It's a weight enumerator. So it's an infinite sum, but it's a formal sum. So it's not really infinite. It has an algorithm to generate for any you look at a coefficient. So when you look at the sum of all the walks, this gives you all the information about the enumeration. If you have an explicit expression for this, you can do the Taylor extension, take the coefficient of t to the power n, take coefficient of x to the j, and this will tell you exactly the number of walks that have n steps and ended up in j. In a special case, when j is 0, the coefficient of x to the power 0, then you get the original problem. The number of good walks that never go negatives, that's this. So my goal in life is to compute it explicitly. Once I have an explicit formula for f of tx, I can hopefully do Taylor extension and get it. So all the information is contained, also enumeration is contained in this formal power series. Formal power series because you don't have to worry about convergence in the sense of Weierstrass and Cauchy. Everything is formal power series. It's a complete algorithm that you can extract the coefficient. So let's derive an equation for f of dx that enables us to maybe generate it on a computer. Let's look at a typical walk. Case 0 is the empty walk. And what's the weight of the empty walk? What's the weight of the empty walk? What's the weight of the empty walk? What's the weight? According to the definition, the weight of W is x is t to the power n times x to the power j, where n is the length of the walk and j is the destination.
So it's 1?
Right?
1?
Yeah, 1. It's t to the power 0 because the empty walk has 0 steps. And x to the power 0 because if you started at 0, you didn't go anywhere, you're still at 0. So it's 1. Let's get 0. Case 1, since the alphabet, the alphabet is only of the letters 1 and minus 1, it ended, W is W1 followed by 1. It ended at 1. So blah, 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 blah. It ended at 1. If you chop it, it's still a good walk. Because of length, 1 less. Conversely, if you take a good walk and add 1 to it, you can never ruin it. It's still. So the one-more correspondence between good walks that end at 1 with length n and good walks that end that any good walk with length n minus 1 that are compared. So the weight, the total weight of this is f of tx times t, because we have an additional time step, times x, because we walked. With the x coordinates, they calculate more. So this takes care of this. So the subset of walks that ended at the step 1 is exactly given by this, assuming you already know f of tx. In case 2, since the alphabet only consists of 2 letters, plus 1 and minus 1, now you have to be careful. If you go backwards, of course it's okay. It's a good walk. If you chop it, it has to be good every step. So if it's good until n, and if you chop it, you have a walk up to, it has to be good until n minus 1. So it's still good. But now be careful, not vice versa. You have to be careful. So you think initially they'll be like this. But you cannot take any old good walk and stick a minus 1 to it. If the walk ended at 0, a good walk, the drunkard made it, you cannot just, it's okay, always safe to obtain the 1. You can never make it bad. But if it's here, you cannot do it. So you have to take away to make it. And you have to take away what? These are the walks that end up at 0. So this is a weighted numerator of all the legal walks that end at -1, because this, take away, this will give us legal. And that's everything! So we have a so-called functional equation. F of dx is 1 plus dx times f of dx plus t times x minus 1. So this is a functional equation because it has 2 variables, t and x. And by the way, I call x a catalytic variable. In order to compute f of t, I'm forced to introduce the other variable x. That may be interesting, but you may not be interested. It's sometimes you're not interested. This is a complete characterization of a desired functional equation. And you can compute it on the computer. You can write a little maker program. This starts with 1 and iterate this mapping. So 1, then you put 1, you get tx, and if you iterate it n times, you get the first n coefficients. So it's an algorithm to generate as many terms as you want, even a good one. But it's not an explicit answer. It doesn't give us the 2n, the Canada numbers yet. And it's not explicit. It's implicit, but not explicit. I want a closed form for f of dx. And here it is. I take my hat, and out of the hat, I pull out the answer. F of dx is given by the following beautiful explicit expression. If you don't mind, spare words. Here it is. I claim that this is the answer. If you don't believe me, go to Maple, or even if you're good at calculation, you can do it by hand. It's not too bad. Plug it in here. This is unique. There's only one unique problem how to introduce it. So, take this, plug it in here, and see if it's true or false. I believe you it's true, unless I made a short mistake. I think it's true. QED. You thus come up with an explicit proposed answer, and since I already derived functional equation, that's it. There are only 2 issues here. One issue, it's not completely obvious that that's a formal power series. If you take a random expression like this and you expand it in part of t, you may get not a Taylor series. So there is a way out of it. I claim it's also routine calculation that f of dx is a solution